Alright guys, today we're going to be doing some problems from the Algebra 2 Research Honors Enrichment problem set. So our first problem is compute a number which is 1,000 more than its additive inverse. So recall that for any number x, the additive inverse is the number negative x, such that x plus negative x equals 0. So we want to find a number which is 1,000 more than its additive inverse. Or in other words, x equals negative x plus 1,000. Right? Now, we can add x to both sides, getting that 2x equals 1,000. Dividing by 2, we get x equals 500. Now, we could confirm that, in fact, 500 is, in fact, negative 500 plus 1,000. And so this answer checks out. We can write that in. The answer is 500. Okay, suppose that a license plate must consist of 3 capital letters. So let's write that out. Let's erase this. 3 capital letters. 1, 2, 3. Followed by 4 digits. 1, 2, 3, 4. Repetition is allowed. Suppose that LOL is a bad word and forbidden on license plates. How many license plates are possible that do not contain the word LOL? So I think the best way to go about this probably is determining the total number of license plates and then the number of license plates that contain the word LOL and then subtracting. So the total number of license plates is, well, the first slot is 26. First 3 slots are 26. And then since we work in base 10, these are all one of 10 options. So the total number of license plates is 26 cubed times 10 to the 4th by basic counting principle. Now, here, this is the total number of license plates that contain LOL. Well, here we only have one slot, which is LOL. And then here we could put any of 10 numbers. So 10, 10, 10, 10. Now, by basic counting principle, our total number of license plates that contain LOL is simply 10 to the 4th. So now subtracting the total number of license plates minus the number of license plates that do contain LOL, we get the total number of license plates that do not contain LOL, and that is our answer, 26 cubed. Okay, here's a tough one. Given x is positive, determine the value of x in simplest form. Oh, okay. So we have an infinite power tower, right? And recall that infinity plus or minus any number is just infinity. Any number a is just infinity, right? So here we have an infinite amount of x's. And observe that x to the x to the x to the x, so on and so forth forever is just 2. But we see that the power that we're raising x to is x to the x to the x to the x, so on forever. So this is just 2, right? So in other words, we're just saying x squared equals 2. And we're given that x is positive, so our solution is x equals the square root of 2 because we're ignoring the negative solution. So this next problem says that 9 congruent rectangles are placed as shown below to form a large rectangle whose area is 180 square inches. What is the perimeter of the large rectangle? So there's 2 ways that we could say what the area of this large rectangle is. Firstly, we could say that the area, not the perimeter, the area, is 9 of these smaller rectangles with an area of xy each. So 9xy equals 180. The second way is using base times height. 4y is the base times the height of x plus y equals 180. Now what we're going to do is we're going to solve for x and y and then get the perimeter. So we could expand out 4y times x plus y into 4xy plus 4y squared equals 180. This is the base times height one, by the way. Okay. Now, we also know that 9xy equals 180. That means that xy equals 20. And here we have xy. So we could rewrite this as 4 times 20 plus 4y squared equals 180. This turns out to be 80. Subtracting that from both sides, we get 4y squared equals 100. Dividing both sides by 4, we get y squared equals 25, and y equals plus or minus 5. Obviously, we need to reject the negative 5, so we get y equals 5. Now, plugging that into our xy equals 20, we get 5x equals 20, and x equals 4. We just plugged in the y equals 5 into xy equals 20. Now, all we need to do is simply compute the perimeter, which we see here we have 1, 2, 3, 4, 5 x's and 4 y's. So 4 times 5 is 20, and 5 times 4 is 20, and we get 20 plus 20 is 40, plus 4 plus 5 is 9, and 4 plus 5 is 9. So 20 plus 20 plus 18, we get an answer of 58. And that is the perimeter of the large rectangle, 58. Given that x is positive, rewrite the x in the form a plus the square root of b over c, where a, b, and c are in the set of integers. So this is very similar to the power tower problem we had over here. So we see that x is the same as 1 over 1 plus 1 over 1 plus 1 over 1 plus, etc. for so on forever and ever. But we see that this is 1 plus 1 over, or 1, sorry, this is x. This is 1 over 1 plus 1 over 1 plus 1 over, etc. so on forever. So in other words, this is simply x equals 1 over 1 plus x. Because this part that I circled in blue is x. This is 1 over 1 plus 1 over 1 plus x. 1 over 1 plus 1 over, yeah, etc. so on forever. So now we could simply solve for x. So we get that 1 plus x times x equals 1. So x plus x squared equals 1, or x squared plus x minus 1 equals 0. Now we can use quadratic formula, so we get that negative 1 plus or minus the square root of 1 squared minus 4 times 1 times negative 1 over 2. Or in other words, negative 1 plus or minus the square root of 5 over 2. And we can reject the negative solution because x is positive, so negative 1 plus the square root of 5 all over 2. So 4 congruent rectangles are placed as shown below. The length of a side of the outer square is 4 times the length of the side of the smaller square. If the area of one of the rectangles is 60 square feet, determine the perimeter of one of the rectangles. So we see that if the length of the side of the smaller square is x, then the larger square side is going to be 4x. Let's call this 4x. So then the area of this big square is 16x squared, and the area of this small square is x squared. So if we subtract the area of the smaller square from the bigger square, we have the area of all 4 rectangles. And since all 4 rectangles are congruent, we see that the area of one of these is going to be the total area of all 4 divided by 4. And that's going to equal 60. Now we see that 15x squared equals 240. Or so we see that x squared equals 15 times x plus 4 times x minus 4. So we get x equals plus or minus 4. But now we're not done because we still have to eliminate this solution. And so we see that x equals 4. Now we need to determine the perimeter. So let's call this little small side, because this 4x is the entire side. So let's call this little tiny piece right here, let's call this h. So this is h, this is h, and this is h. First, we can substitute. So since we know x equals 4 now, let's rewrite these all in terms of an actual whole number. So we know that this is 4, and this whole side is 16. So let's actually erase all this stuff just to clean it up a bit. So we'll only worry about one of these. So 4, this side is 4, then this whole thing is 16, and this is going to be h, and this is going to be h. And let's say this is h2. So then this side is going to be 16 minus h. And remember that the area is 60 square feet. So let's solve for the area, and then we can solve for the perimeter. So 4 plus h times h equals 60. So we get 4h plus h squared equals 60. So subtracting 60 from both sides, we get 4h squared plus 4h minus 60 equals 0. And so this becomes h minus 6 times h plus 10. And so we could reject this solution, and we get h equals 6. So now let's substitute that in. We get 6. This is, right here is 6, 6, 6, and this is 10. So we get an area of 10 plus 12 plus 10, or perimeter of 10 plus 12 plus 10, 32. So the perimeter of one of the smaller rectangles is 32. Okay, if 7 to the n divides 77 factorial, determine the largest possible integer value of n. So first let's figure out how many multiples of 7 are in 77 factorial. And to do that, we can just divide 77 by 7, and we get 11. But notice that one of those is 7 squared, which counts as 2 factors. So really, this is 11 plus 1 equals 12. In other words, there are 12 different multiples of 7 that divide 77 factorial. And so, in other words, our answer is 12. Kind of underwhelming, actually. Solve for x in simplest form. 2 to the 16 to the x equals 16 to the 2 to the x. So, originally, I thought this was a logarithm problem, but then I remembered that 16 to the 2 to the x, well, 16 is just 2 to the 4th, so this is really just 2 to the 4th to the 2 to the x. And, in other words, we could write this as 2 to the 4 times 2 to the x. But 4 is just 2 squared, so this is just 2 to the 2 squared times 2 to the x, or 2 to the 2 to the x plus 2. Cool. So, now in other words, we have 2 to the 16 to the x equals 2 to the 2 to the x plus 2. And since our bases are equal, we could write this as 2 to the x plus 2 equals, sorry, I flipped them around, this is this, equals 2 to the x plus 2. 2 to the, sorry, 16 to the x plus 2. 16 to the x, sorry, again. Well, remember 16 is just 2 to the 4, so we have 2 to the x plus 2 equals 2 to the 4 to the x, or 2 to the x plus 2 equals 2 to the 4x. Now we reduce this to a really simple linear equation. X plus 2 equals 4x. So subtracting x, we get 3x equals 2. And now x equals 2 over 3. Alright, this next one looks pretty cool. So the cube root of, or the 6th root of the cube root of x to the 4th times the x to the 9th root, the square root of the 9th root of x to the 5th. And we need to express this in simple radical form. I think the best way to go about this is to re-express this as a fractional exponent. So x to the 1/3 times, or to the 1/6 to the 4. And so that's x to the 4 over 18 times, now this is x to the 5th to the 1/9 to the 1/2. And that is x to the 5 over 18. So x to the 5 over 18 times x to the 4 over 18 equals x to the 9 over 18, which is just x to the 1/2, or the square root of x. Now, this next one, for what is the real value of x, for which the cube root of x times the square root of x equals 4. So we could do this in the same way as we did this, but I think it'd be easier to just cube both sides to get x times, let's use fractional exponents, x to the 1/2 equals 4 cubed, so 64. So now we get x to the 3 over 2 equals 64. Let's raise both sides to the 2 over 3 so we get x by itself. So we get x equals 64 to the 2 over 3. Or, in other words, x equals the cube root of 64 squared. Given that x is positive, solve for x in simplest form. This is very similar to the other two problems we did with the power tower and this one right here where we had 1 over 1 plus 1 over 1 plus etc. So, we know that x is equal to the square root of 1 plus the square root of 1 plus the square root of 1 plus forever and ever. And we see that we have x inside of itself. We have the square root of 1 plus the square root of 1 plus inside of itself forever right here. So this is just the square root of 1 plus x equals x. Let's square both sides to get 1 plus x equals x squared. Now let's subtract x squared from both sides to get x squared, or let's subtract x from both sides, so we get x squared minus x minus 1 equals 0. And I believe we had that same exact thing right over here. Yeah, oh no, something very similar. Ignore that then. So we could solve this with the quadratic formula. Oh, went too far. We could solve this with the quadratic formula, and we could get 1 plus or minus the square root of 1 minus 4 times negative 1 all over 2, and we get 1 plus or minus the square root of 5 over 2. It says given the x is positive, so 1 plus the square root of 5 over 2 is our solution. We're trying to find all the values of x which satisfy x squared minus 5x plus 5 to the power of x squared minus 9x plus 20 equals 1. Now, there are a couple cases we can consider. The first one being that a equals 1, equation a equals 1, and equation b equals any number, n. The second case is that a equals any number, n, and b equals 0. Now, the third case, which many people probably won't think about, is that this equation, a equals negative 1, and b equals some even number, 2k, because even numbers are all in the form 2k. So, to make this easy, I just took the natural log of both sides. So, natural log of x squared minus 5x plus 5 to the power of x squared minus 9x plus 20 is x squared minus 9x plus 20 times the natural log of x squared minus 5x plus 5. Natural log of 1 is 0. So now, one of the cases in which this equation would be equal to 1 is the case where x squared minus 5x plus 5 equals 1. Because in that case, the natural log of x squared minus 5x plus 5 would equal 0. So, now, we could write this as x squared minus 5x plus 5 equals 1. Subtracting 1 from both sides, we get x squared minus 5x plus 4 equals 0. Now, let's factor this as x minus 1 times x minus 4. And now that would give us 4 or 1. And keep in mind, this works because if this equation inside the natural log equals 1, that would set the natural log of x squared minus 5x plus 5 to 0, and then that would set this whole equation equal to 0, and that would be a valid solution because keep in mind these two are equivalent, these two equations. So x squared minus 5x plus 5 to the x squared minus 9x plus 20 equals 1, and x squared minus 9x plus 20 times the natural log of x squared minus 5x plus 5 equals 0. If we can find a solution to this, we get a solution to this for free. So we get 1 and 4 are two of our solutions. Now, let's consider when this equals 0. So x squared minus 9x plus 20. Now, it turns out that there are two cases in which this equals 0. X equals 4 and x equals 5. So we already have 4, so let's add 5 to our solution set. But we're not done yet. We still need to consider the case where x squared minus 5x plus 5 is negative 1. So, and when x squared minus 9x plus 20 is an even integer. So, when x squared minus 9x plus 20 is an even integer, this forces x squared minus 5x plus 5 to equal negative 1. So x squared minus 5x plus 5 equals negative 1. And so now we could add 1 to both sides, getting x squared minus 5x plus 5 to be equal to 0, plus 6 to be equal to 0. Let's factor this as x minus 2 and x minus 3. And we get x equals 2, 3. Now we have two more solutions, and that is all the solutions. 2, 3, 4, 5. Now, we know that there are 5 values that satisfy these equation 1, 2, 3, 4, and 5. Thank you for watching. Yeah, bye.